So this is a very similar setup to the previous question, only this time we're using a sphere instead of a cylinder. So the center of the sphere to the outer surface will be represented by R. Show this as a sphere. And like last problem, we're only focused on one half of the sphere. And we're also only focused on all of the horizontal forces acting upon that surface. And so we still need to find that horizontal force in terms of tensile strength. And so very similar process, we just multiply both sides by A. The area, the surface area in this case, will be 2 pi RT times sigma, with T being the thickness of that wall it's pushing against. And so in order to show off what that force looks like, I'm going to draw a graph with the X, Y, and Z planes. And so we're representing that force as a vector at a given point, this graph. And so that vector force is pushing against a little chunk of that sphere. And so we need to find that surface area at which that force is pushing against. So let's get some values established. I'm going to represent the angle from the force, or the angle relative to that force vector to that xy plane. That angle between the force and the xy plane will be theta, and the angle relative to the x plane or y plane, however you want to represent it, or no, just x plane, I don't know what I'm saying, would be just theta. And so we need to find the surface area, right? And so just like the previous problem, we need to find the arc length of this section right here. And it's basically exactly the same. We need to find d theta, multiply that by r, and you can get the arc length r d theta. We're using d theta because it is relative to the xy plane. That angle is relative to that plane. So now we also need to find this horizontal distance from the center to that surface area. And just like that other problem, that distance would be r cosine theta. We also need to remember that there's variance in phi, the angle relative to the x-plane. That angle will change depending on where that vector is located, and that can be represented as d phi. And so putting all those together, you can get the equation r cosine theta times this by r d theta times this by d phi. We can simplify this a little more. R squared times this by cosine theta d theta times d phi. In this scenario, we're focused on the force pushing against that surface area of the tank, right? But that force only represents the normal force relative to that surface we're accounting for. But we need to find the horizontal component instead, so we set that up as df of x, d of f representing that force pushing against the surface, times that by cosine theta times, I didn't write that, cosine phi, because we're finding that horizontal component according to those two angles, right? More. We can rewrite this equation, d of f is equal to pdA, but we already found pdA, so we just plug that in place of that, cosine theta, d theta, d phi, that's another theta, and then we multiply it by cosine theta times that by cosine phi. Again, we can simplify that a little more. PR squared cosine theta times this by cosine squared theta cosine phi, then d theta d phi. There we go. So now we need to find the integral of both sides. Finding the integral of df of x will give us f of x. So now we have an equation to set it equal to this equation. That comes later. We still need to integrate the other side. So p r squared, those are constants, so those stay outside the integrals. And so the bounds are going to be the same because we're taking it from the bottom half of the sphere to the top half of the sphere. We can use negative pi over 2 to pi over 2, create an integral based off of theta. We also need to create an integral for phi because that angle also varies between vectors. So we use the same bounds, and then we cosine phi times, or just d phi. There we go. So now we need to simplify this equation, find the integrals. So starting off with this, it's exactly the same as the previous problem. The integral of cosine phi is just sine phi. We use the same bounds for this equation as well. Plugging those values in, sine pi over 2 is just 1 minus sine negative pi over 2 is negative 1. That'll be 2. So this entire integral is equal to 2. Now we need to find the integral of this. It's going to be a little more complicated because we need to use UV substitution, or integration by parts, I mean. So let me set this up like this. U dv, v du. U is going to be cosine theta, dv, cosine, I don't know why it's doing that. Cosine theta, d theta, v is equal to sine theta, and du is equal to negative sine theta, d theta. And so we need to find this integral using I just said whatever. Substitution by parts, that's what the name is. Gosh, my brain is fried. So we need to use substitution by parts to solve this equation. So this will be equal to uv minus v du, and that would be cosine theta times this by sine theta minus sine times negative sine theta d theta. So this would be sine squared theta d theta, but since there's a negative sign, we multiply that against each other. It's going to be negative in there, but we can move that and just make this plus. And the bounds for these two parts are going to be the same like normal. It's going to be negative pi over 2. Stop doing that. Negative pi over 2 to pi over 2. Okay. So looking at this integral, plugging in either pi over 2 or negative pi over 2 into cosine would just give you 0, and then multiply that by sine theta, it still gives you 0. So for both parts, you would just get 0 minus 0. So this entire part is 0, so we can basically just erase that part. Let me actually just erase that, create less confusion. So now we're just left with the integral of sine squared theta d theta. So this has an identity of 1 minus cosine squared theta. And so we can basically split this off into two separate integrals. So let's get rid of that real quick. So this will be equal to integral of 1 d theta minus cosine squared theta d theta with the same bounds. I'm just not going to write for, I'm too lazy. So we can actually move this integral to this side, and that'll give us 2 of the same integral, so we can just put a 2 in front of it to represent that there were 2 of the same integrals, and rewrite the equation even more. And all we have left on this side is 1 d theta with the bounds, oh my gosh, with the, come on, with the bounds negative pi over 2 to pi over 2. And so, since we need to find a replacement for this equation, which is the same as this part right here, we need to solve for this right side, just 1 d theta. So, my goodness, come on. So 1 d theta, you integrate that, you just get theta with the bounds negative pi over 2 to pi over 2, and plugging those values in, you get, well, negative pi over 2 minus negative pi over 2, which is just pi, but we also need to divide both sides by 2 in order for cosine squared d theta to get isolated. So we divide both sides by 2, so divide this side by 2, divide this side by 2, you're left with pi over 2. So now we have an equation, or an answer for this integral. It's going to be pi over 2. Okay, now we can rewrite this equation using this new information we have. Eraser, f of x will be equal to pr squared times this by pi over 2 times this by 2. And so now we can cancel out these 2's, and now we're left with pr squared times this by pi. And this is f of x, all the forces in the x direction. So now we can set this equal to this equation we found earlier. So we have 2 pi r t theta, or not theta, sigma, sorry. Set this equal to the expression we found just now, pr squared times pi. We can cancel out some values. We cancel out the pi's, we cancel out an r, and now again we're finding the thickness needed. So that expression, you just rearrange the equation a bit, and you're left with t is equal to pr divided by 2 sigma.